Hello there, and welcome to Smart Student TV, the only channel where academic and professional prowess is nurtured right from the comfort of your living room. Whether you are a student striving for excellence, a professional looking to sharpen your skills, or simply a lifelong learner, you are in the right place. In today's tutorial, we dive into another very crucial topic: laboratory waste management. Laboratories are the heart of scientific discovery, medical diagnostics, and industrial innovation. However, alongside the vital work performed in these facilities comes an often overlooked byproduct: laboratory waste. Laboratory waste refers to any unwanted or discarded material generated from laboratory activities, including research, diagnostics, testing, and production. This waste can range from harmless general waste to highly hazardous chemical, biological, or radioactive materials. Laboratory waste management is not just about keeping the lab clean. It is a critical practice to protect human health, ensure environmental safety, and comply with regulatory requirements. Poor waste management can lead to chemical spills, biological hazards, environmental pollution, and even legal consequences. Therefore, every lab technician must understand the importance of proper waste handling, segregation, and disposal. Objectives of this tutorial. By the end of this tutorial, you will be able to 1. Understand laboratory waste management. Gain a comprehensive understanding of what laboratory waste management entails. 2. Recognize the importance. Identify why proper laboratory waste management is crucial for safety and sustainability. 3. Classify laboratory waste. Learn the different types of laboratory waste and their sources. 4. Explore waste management methods. Understand the various methods for managing and disposing of lab waste. 5. Implement waste segregation practices. Learn the correct ways to segregate different types of waste using appropriate disposal bins. 6. Adopt best practices. Develop skills to incorporate waste management best practices in day-to-day lab activities. Objectives of laboratory waste management. The objectives of laboratory waste management are aimed at ensuring safety, compliance, and sustainability within laboratory environments. These objectives include: 1. Ensuring safety. Protect laboratory personnel, students, and visitors from exposure to hazardous waste materials. 2. Environmental protection. Prevent contamination of soil, water, and air by ensuring proper waste disposal. 3. Regulatory compliance. Adhere to national and international laws and guidelines governing waste management. 4. Waste reduction. Minimize waste generation through efficient laboratory practices. 5. Resource optimization. Promote recycling and reuse of materials where possible. 6. Public health protection. Prevent the spread of infectious diseases caused by improper handling and disposal of biological waste. 7. Training and awareness. Educate lab personnel on best practices for waste handling, segregation, and disposal. By meeting these objectives, laboratories can create a safe working environment, reduce environmental risks, and contribute to a more sustainable future. Importance of laboratory waste management. Effective laboratory waste management has multiple layers of importance, each contributing to a larger goal of health, safety, and sustainability. First and foremost, managing lab waste protects laboratory personnel from exposure to harmful chemicals, infectious agents, and sharp objects. For instance, improperly disposed needles and glass shards can cause injuries and infections. Beyond personal safety, waste management reduces the risk of environmental pollution. Chemicals leaching into the soil or waterways can disrupt ecosystems, contaminate drinking water, and pose long-term health risks to communities. For example, mercury waste from a chemistry lab, if not properly disposed of, can enter water systems and bioaccumulate in fish, eventually harming human consumers. Moreover, adhering to waste management protocols ensures compliance with local and international regulations. Laboratories operate under strict guidelines from bodies such as OSHA, Occupational Safety and Health Administration, and the EPA, Environmental Protection Agency. Failure to meet these standards can result in hefty fines, legal battles, and, in extreme cases, shutdowns. Benefits of effective laboratory waste management. When laboratory waste is managed properly, everyone benefits: the staff, the institution, and the environment. Some key benefits include 1. Enhanced safety, reduced risk of chemical spills, infections, and physical injuries. 2. Environmental protection, prevention of toxic chemical leaks into soil, water, and air. 3. Regulatory compliance, avoidance of legal penalties and reputational damage. 4. Cost savings, proper segregation and recycling can reduce waste disposal costs. 5. Improved lab efficiency. A clean and organized lab environment fosters productivity and reduces clutter. Why some lab technicians do not properly manage waste. Despite the clear benefits, waste management in laboratories often falls short. Some common reasons include 1. Lack of training. Many lab personnel are not adequately trained on waste disposal protocols. 2. Resource constraints. Limited budgets may restrict access to proper waste disposal facilities. 3. Complacency. In some labs, waste management is viewed as a low-priority task. 4. Insufficient supervision. Poor enforcement of waste management policies leads to neglect. Consequences of poor laboratory waste management. The consequences of neglecting waste management in laboratories can be severe and far-reaching. These include 1. Health risks, exposure to toxic chemicals, infectious agents, and sharp injuries. 2. Environmental pollution, contaminants leaching into ecosystems. 3. Legal penalties, fines and legal action from regulatory authorities. 4. Reputation damage, loss of trust and credibility for institutions. Hierarchy of laboratory waste management. To address these challenges, laboratories follow a structured waste management hierarchy. 1. Prevention. Minimize waste generation at the source. 2. Reduction. Reduce the volume and toxicity of waste produced. 3. Reuse. Identify opportunities to reuse materials safely. 4. Recycling. Reprocess waste into usable forms. 5. Treatment. Neutralize hazardous components. 6. Disposal. Safely dispose of waste that cannot be treated or recycled. Clearly, the best approach to laboratory waste is preventing its generation. Examples include reducing the scale of laboratory operations, reducing the formation of waste during laboratory operations, and substituting non-hazardous or less hazardous chemicals in chemical procedures. The initial responsibility for implementing this hierarchy rests with trained laboratory personnel. These individuals are in the best position to know the chemical and physical properties of the materials they have used or synthesized. They are responsible for evaluating hazards, providing information necessary to make an accurate waste determination, and assisting in the evaluation of appropriate strategies for management, minimization, and disposal. Nonetheless, the overriding principle governing the prudent laboratory waste management is that no activity should begin unless a plan for the management of waste, whether non-hazardous or hazardous, has been formulated. How to reduce laboratory waste. In order to minimize the amount of hazardous waste presented for disposal, it is important to follow these guidelines. 1. Avoid overstocking. One of the main sources of laboratory waste is oversurplus stock, the result of overbuying. 2. Buy only what is needed. 3. Do not accept donations of materials that you don't plan to use. 4. Find a reliable supplier who will deliver small amounts of chemicals at short notice. 5. Have a centralized purchasing system. 6. Label all chemicals and wastes in the lab. 7. Separate waste into the following streams for treatment, reuse, or disposal. A. Sharps including scalpels and syringes. B. Broken glassware. C. Biological samples. D. General lab waste. F. Chemicals waste. How to reuse laboratory waste. 1. Reusing an item is often the best way of reducing waste. 2. All waste should be segregated based on chemical incompatibilities, e.g. hazardous and non-hazardous wastes should not be mixed together. The same is true of organic and inorganic waste. 3. Waste streams that are capable of being recycled should be stored separately, i.e. recoverable metals or solvents. How to recycle laboratory waste. 1. Non-hazardous waste such as paper and packaging waste that can be recycled. To promote and encourage recycling of this material, place recycling bins in the lab. 2. Make sure the recycling bin is labeled clearly by placing a label on the bin stating paper only, ensuring that hazardous wastes such as chemicals are not placed in the bin. 3. Bins for the collection of hazardous materials should be placed in the lab. These should be emptied regularly and looked after by lab personnel/technicians. 4. All waste from the lab should be collected by a trained waste collector who is specialized in hazardous waste collection and who is licensed to treat and dispose of the waste. Types of laboratory waste. Laboratory waste can be categorized into several types, each requiring specific handling methods. 1. General waste. Consists of non-hazardous waste such as paper, plastics, and packaging. 2. Chemical waste. Include acids, bases, solvents, heavy metals. 3. Biological waste. Consists of cultures, tissues, and infectious materials. 4. Biomedical waste. Mostly comprising human and animal tissues, syringes. 5. Medical waste, e.g. sharps, contaminated gloves, surgical instruments. 6. Electronic waste. They include electric circuits and electronic components from broken laboratory equipment, computers. 7. Radioactive waste. Usually consist of radiation-generating substances and contaminated equipment, isotopes. 8. Sharps. This consists of all those items that can cause injury by way of cuts, injections, etc., e.g. needles, blades, broken glass. 9. Infectious waste. Consist of items contaminated with pathogenic organisms, e.g. with bacteria, virus, fungi, protozoa, etc. Laboratory waste management for chemical waste. Chemical waste refers to any unwanted or leftover chemical substances, byproducts, or residues generated from laboratory processes, industrial activities, or other chemical-related operations. These wastes can exist in solid, liquid, or gaseous forms and may pose significant risks to human health and the environment if improperly managed. Chemical wastes are typically characterized by properties such as toxicity, corrosivity, flammability, and reactivity. 2. Types and examples of chemical waste. Chemical waste can be categorized based on its properties and hazards. The primary types include abtoxic waste, substances harmful or fatal when ingested, inhaled, or absorbed through the skin. Example: mercury compounds, lead salts, cyanides, etc. B. Corrosive waste. Chemicals that can destroy or irreversibly damage other substances upon contact. Example: sulfuric acid, hydrochloric acid, sodium hydroxide, etc. C. Flammable waste. Chemicals that can easily catch fire. Example: ethanol, acetone, diethyl ether, etc. D. Reactive waste. Chemicals that can cause explosions, release toxic gases, or react violently with water or other chemicals. Example: sodium metal, potassium cyanide, etc. E. Persistent and bioaccumulative chemicals. Substances that remain in the environment for long periods and accumulate in living organisms. Example: polychlorinated biphenyls, PCBs, etc. 3. Sources of chemical waste. Chemical waste in laboratories originates from various sources, including A. Research and development laboratories, experimental chemical processes, reagent preparation, and sample analysis. B. Teaching laboratories, practical exercises, demonstrations, and experiments. C. Pharmaceutical and biochemical laboratories, drug synthesis, quality control, and biological assays. D. Industrial laboratories, product testing, quality assurance, and chemical synthesis. E. Cleaning and maintenance activities, use of solvents, disinfectants, and acids for equipment cleaning. 4. Health effects of chemical waste. Exposure to chemical waste can have acute and chronic health effects, depending on the type, concentration, and duration of exposure. A. Acute effects. Immediate health effects such as skin burns, eye irritation, respiratory distress, nausea, and dizziness. B. Chronic effects. Long-term health issues such as cancer, liver and kidney damage, neurological disorders, and reproductive toxicity. See environmental impact. Contamination of water, soil, and air can harm ecosystems and bioaccumulate in the food chain. 5. Chemical waste management in laboratories. Proper management of chemical waste is essential to prevent health hazards and environmental pollution. Key strategies include A. Waste segregation. Separate chemical wastes based on their properties, e.g., flammable, corrosive, toxic, to prevent reactions. B. Proper labeling. Label all waste containers clearly with information about the contents, hazards, and date of disposal. Sieve storage. Use compatible and leak-proof containers for chemical waste storage. D. Inventory control. Keep track of chemical stock to minimize overpurchasing and waste generation. E. Training. Educate laboratory personnel on safe handling, storage, and disposal practices. 6. Specific management techniques for different types of chemical waste. A. Corrosive chemicals. Store corrosive chemicals in well-ventilated areas away from incompatible substances. Use polyethylene or glass containers resistant to corrosion. Neutralize acids and bases before disposal, if permissible. Ensure spill kits with neutralizing agents are readily available. B. Flammable chemicals. Store flammable chemicals in fireproof cabinets. Keep them away from ignition sources such as open flames and electrical equipment. Use grounding and bonding techniques during transfers. Dispose of flammable waste in approved containers. C. Reactive chemicals. Store reactive chemicals in isolation, away from incompatible chemicals. Use inert gases for storage when necessary. Follow proper protocols for handling and disposal. Do not mix reactive chemicals during disposal. D. Fuming chemicals. Store in ventilated fume hoods or specialized cabinets. Use airtight containers for transport and storage. Dispose of fuming chemicals under controlled conditions. E. Explosive chemicals. Store explosive chemicals in specialized storage cabinets. Minimize the quantity of explosive chemicals in the lab. Dispose of through professional hazardous waste disposal services. F. Poisonous chemicals. Label and store under lock and key in a secure, ventilated locations. Avoid skin contact and inhalation during handling. Dispose of in sealed containers marked as hazardous waste. G. Photosensitive chemicals. Store in dark, opaque containers. Limit exposure to light. Dispose of appropriately in light-restrictive containers. H. Reducing agents. Store separately from oxidizing agents. Ensure containers are properly sealed to prevent reactions. Dispose of via neutralization methods. I. Oxidizing agents. Store in cool, dry areas away from flammable and reducing agents. Use non-reactive storage containers. Dispose of according to regulatory guidelines. 7. Methods for disposing of chemical waste. The disposal of chemical waste must comply with local regulations and environmental laws. Common disposal methods include A. Chemical treatment, neutralization of acids and bases, oxidation or reduction reactions to render chemicals less hazardous. B. Incineration, controlled burning of flammable and toxic waste at high temperatures. C. Landfilling, disposal in secure, lined landfill sites designed for hazardous waste. D. Recycling and reuse, reclaiming chemicals that can be purified and reused. E. Third-party disposal services, hiring certified waste disposal companies. 8. Conclusion. Effective laboratory chemical waste management is crucial for protecting human health and the environment. Proper segregation, labeling, storage, and disposal, combined with staff training and adherence to regulations, are key to minimizing the risks associated with chemical waste. Laboratories must prioritize sustainable practices and aim to reduce waste generation through better resource management and recycling initiatives. Next, let's look at management of biological, biomedical, and infectious waste. Biological, biomedical, and infectious waste management is a critical aspect of healthcare and environmental safety. With the rapid growth of healthcare facilities, laboratories, and research institutions, the volume of waste generated has significantly increased. Proper management and disposal of these wastes are essential to prevent health hazards, environmental pollution, and the spread of infectious diseases. 2. What are biological, biomedical, and infectious waste? Biological waste refers to waste materials that are derived from living organisms. These include tissues, organs, blood, bodily fluids, and other organic materials. Biological waste can originate from hospitals, research laboratories, and veterinary clinics. Biomedical waste, on the other hand, is a subset of biological waste and includes any waste generated during the diagnosis, treatment, or immunization of humans or animals. It also includes waste generated during research activities, production, and testing of biologicals. Infectious waste refers specifically to waste that contains pathogens or microorganisms capable of causing disease in humans or animals. This type of waste poses a significant health risk and requires specialized handling and disposal. Examples of biological, biomedical, and infectious waste. 1. Human tissues and organs. 2. Blood and blood products. 3. Syringes, needles, and sharps. 4. Laboratory cultures and stocks of infectious agents. 5. Bandages, dressings, and cotton swabs. 6. Pharmaceutical waste. 7. Animal carcasses and tissues from veterinary clinics. 8. Infected personal protective equipment, PPE. 9. Isolation ward waste from contagious patients. 3. Sources of biological, biomedical, and infectious waste. The primary sources of biological, biomedical, and infectious waste include 1. Hospitals and clinics. Diagnostic and treatment procedures generate waste such as syringes, blood, and infected materials. 2. Research laboratories. Experimental processes produce cultures, samples, and contaminated equipment. 3. Veterinary clinics. Animal treatment and surgeries result in carcasses, organs, and blood waste. 4. Pharmaceutical companies. Manufacturing and testing generate chemical and biomedical waste. 5. Household healthcare. Home-based care involving syringes, bandages, and medicines contributes to biomedical waste. 6. Quarantine centers. Isolation and treatment of contagious patients generate highly infectious waste. 4. Health hazards associated with biological, biomedical, and infectious waste. Improper handling and disposal of biological, biomedical, and infectious waste pose significant health hazards, including 1. Spread of infectious diseases such as HIV, hepatitis B and C, and tuberculosis. 2. Injuries from sharps like needles and broken glass. 3. Chemical exposure causing poisoning, burns, and respiratory issues. 4. Antibiotic resistance from the improper disposal of pharmaceuticals. 5. Environmental contamination affecting water, soil, and air. 6. Spread of pandemics through improper disposal of infectious waste. 5. Procedures for management and disposal of biological, biomedical, and infectious waste. Effective management of biological, biomedical, and infectious waste involves a series of systematic steps, which include 8. Segregation. Waste must be segregated at the point of generation. Different colored bins are used to categorize waste. Red bins, used for holding highly infectious wastes, e.g. human and animal anatomical waste, and other infectious waste. Yellow bins, for holding moderately infectious waste, e.g. contaminated waste like syringes, soiled cotton wool, bandages, for tubes. Blue bin, for holding non-hazardous general waste, e.g. glassware and metallic body implants. Black bin, for holding general lab waste. Beet collection and storage. Waste should be collected in designated containers and stored in a safe, labeled area away from public access as soon as they are generated. C. Transportation. Biomedical and infectious waste should be transported in specially designed vehicles to prevent spillage and exposure. D. Treatment and disposal methods. 1. Incineration. Used for disposal of anatomical, pharmaceutical, and infectious waste. 2. Autoclaving. Used for sterilizing reusable equipment and infectious materials. 3. Microwaving. This method is specifically used to reduce microbial load on an item or media. 4. Chemical disinfection. This method is specifically applied to liquid waste, infectious waste, and sharps. 4. Land disposal. In this method, a secured landfill is identified and used for disposal of non-hazardous waste. 6. Regulatory framework and guidelines. Many countries have established regulations for biomedical and infectious waste management. For instance, 1. WHO Guidelines on Biomedical and Infectious Waste Management. 2. Biomedical Waste Management Rules, e.g., India, 2016. 3. OSHA Standards, USA. 7. Role of awareness and training. Healthcare workers, waste handlers, and support staff must be trained in waste management protocols. Public awareness campaigns can also help reduce risks associated with biomedical and infectious waste. 8. Conclusion. The management of biological, biomedical, and infectious waste is essential for public health and environmental safety. Strict adherence to waste disposal guidelines, regular monitoring, and awareness programs can ensure effective waste management practices. Governments, healthcare facilities, and individuals must work together to minimize the risks associated with improper waste disposal. Now let's shift focus and look at management of sharps. Among the various types of laboratory waste, sharps represent a significant category due to their potential to cause physical injury and transmit infections. Proper management and disposal of sharps are critical to minimizing risks associated with their use and disposal. 2. What are sharps? Sharps refer to any objects or instruments capable of puncturing or cutting the skin. In laboratory settings, sharps typically include items such as needles, syringes with needles, scalpel blades, lancets, broken glass, microscope slides, pipette tips, and any other sharp-edged tools. These items are commonly used in medical, biological, and chemical laboratories for a variety of procedures, including sample collection, chemical analysis, and microbial testing. 3. Contaminated sharps. Contaminated sharps are sharp objects that have come into contact with biological, chemical, or radioactive materials, making them hazardous. Examples include 1. Needles used for drawing blood or administering medications. 2. Scalpel blades used in tissue dissection. 3. Glass slides used for microbiological analysis. 4. Pipette tips exposed to infectious agents. 4. Sources of contaminated sharps. The sources of contaminated sharps in laboratories are diverse and depend on the type of work being performed. Common sources include 1. Medical and clinical laboratories. Needles, syringes, and scalpels used in specimen collection and diagnostic procedures. 2. Microbiology laboratories. Pipette tips, microscope slides, and needles used in inoculation procedures. 3. Chemistry laboratories. Broken glassware, sharp-edged tools, and contaminated glass slides. 4. Research laboratories. Experimental setups involving biological agents, radioactive substances, or hazardous chemicals. 5. Health effects of contaminated sharps. Exposure to contaminated sharps can pose serious health risks to laboratory personnel and waste handlers. Potential health effects include 1. Transmission of blood-borne pathogens. Diseases such as HIV, hepatitis B, HBV, and hepatitis C, HCV, can be transmitted through needle-stick injuries. 2. Chemical exposure. If sharps are contaminated with hazardous chemicals, exposure can result in chemical burns, poisoning, or long-term health effects. 3. Infections. Bacterial, fungal, or viral infections can occur if pathogens are introduced into the body through sharp injuries. 4. Psychological impact. Fear and anxiety following an injury from a contaminated sharp object can affect mental health. 5. Management of sharps. Proper management of sharps in laboratories is essential to prevent injuries and ensure compliance with safety regulations. Key management practices include 1. Use of appropriate containers. Sharps should be disposed of in designated, puncture-resistant, leak-proof containers that are labeled with biohazard symbols. 2. Immediate disposal. Sharps should be disposed of immediately after use to prevent accidental injuries. 3. Segregation of sharps. Sharps should not be mixed with general laboratory waste. They should be collected separately. 4. Training and awareness. Laboratory personnel must be trained in the safe handling and disposal of sharps. 5. Use of safety devices. Safety-engineered sharps, such as retractable needles and self-sheathing scalpels, should be used whenever possible. 7. Disposal of sharps. The final disposal of sharps is a critical aspect of their management. Disposal methods vary depending on the level of contamination and regulatory requirements. 1. Autoclaving. Contaminated sharps can be sterilized using high-pressure steam to eliminate infectious agents before disposal. 2. Incineration. Sharps contaminated with hazardous biological or chemical materials are incinerated at high temperatures to ensure complete destruction. 3. Chemical disinfection. Certain sharps can be treated with chemical disinfectants to neutralize infectious agents before disposal. 4. Sharps containers. Once full, sharps containers should be securely closed and disposed of through licensed biomedical waste management services. 5. Regulatory compliance. Laboratories must adhere to national and international regulations governing sharps disposal. 8. Conclusion. Safe laboratory waste management for sharps is a fundamental aspect of laboratory safety and environmental protection. Proper handling, segregation, treatment, and disposal of sharps minimize the risk of injuries and infections. Continuous training, adherence to safety protocols, and compliance with regulations are essential components of effective sharps waste management. By prioritizing these measures, laboratories can create a safe working environment and prevent adverse health outcomes associated with improper sharps disposal. Laboratory waste management for radioactive waste. Radioactive waste refers to materials that emit radiation and are no longer useful for their intended purpose. These wastes arise from activities involving radioactive substances, such as nuclear power generation, medical treatments, industrial applications, and research laboratories. Radioactive waste can pose significant health and environmental hazards if not handled and disposed of properly due to its ionizing radiation, which can damage living tissues and DNA. 2. Types and examples of radioactive waste. Radioactive waste is categorized based on its origin, level of radioactivity, and half-life of the radioactive isotopes. These categories include 1. Low-level waste, LLW, contains low levels of radioactivity. Examples include contaminated gloves, paper towels, and protective clothing. 2. Intermediate-level waste, ILW, contains higher levels of radioactivity but generates minimal heat. Examples include reactor components and chemical sludge. 3. High-level waste, HLW, highly radioactive and generates significant heat. This typically comes from spent nuclear fuel rods. 4. Exempt waste, contains very low levels of radioactivity and poses minimal risk. Examples include certain laboratory glassware and tools. 3. Sources of radioactive waste in laboratories. Radioactive waste in laboratories primarily originates from 1. Medical research, especially during use of radioisotopes in diagnostic imaging and cancer treatment. 2. Academic research, originating during experiments involving radioactive tracers and radiochemical analyses. 3. Industrial applications, as a result of testing materials for structural integrity and quality control using radioactive sources. 4. Nuclear research, while working in experiments involving reactor fuels and nuclear reactions. 4. Health effects of radioactive waste. Exposure to radioactive waste can lead to acute and chronic health effects. 1. Acute effects, radiation sickness, skin burns, and acute radiation syndrome. 2. Chronic effects, cancer, genetic mutations, and long-term organ damage. 3. Environmental impact, contamination of soil, water, and air, leading to bioaccumulation in plants and animals. 5. Laboratory management of radioactive waste. Proper management of radioactive waste in laboratories is essential to prevent exposure and environmental contamination. Key practices include 1. Segregation. Different types of radioactive waste must be segregated based on their level of radioactivity and half-life. 2. Labeling. Containers must be clearly labeled with the type of waste, radioisotope, and activity level. 3. Storage. Use shielded and ventilated storage facilities designed for specific waste types. 4. Personal protective equipment, PPE. Lab personnel must wear appropriate PPE, including lead aprons, gloves, pocket dosimeters, and radiation film badges. 5. Training and education. Regular training on radioactive waste handling and emergency response. 6. Disposal methods for radioactive waste. Radioactive waste disposal depends on the type and level of radioactivity. 1. Decay in storage, DIS, allowing short-lived radioactive materials to decay to safe levels before disposal as regular waste. 2. Incineration, controlled burning of low-level radioactive waste to reduce volume. 3. Deep geological disposal, burying high-level waste in deep, stable geological formations. 4. Surface or near-surface disposal, burying low and intermediate-level waste in engineered facilities. 5. Recycling and reuse. In some cases, radioactive materials can be reused or repurposed. 7. Conclusion. Effective management of radioactive waste in laboratories is essential to protect human health and the environment. By implementing strict safety protocols, proper waste segregation, and appropriate disposal techniques, laboratories can minimize the risks associated with radioactive waste. Continuous education and adherence to regulatory guidelines are key to ensuring safe and sustainable radioactive waste management practices. Finally, let's discuss electronic waste management in the laboratory. Electronic waste, commonly referred to as e-waste, encompasses discarded electrical or electronic devices. These devices are no longer functional, have become obsolete, or are simply unwanted. With the rapid advancement in technology and the decreasing lifespan of electronic products, e-waste has become one of the fastest-growing waste streams globally. Laboratories, being technology-intensive environments, contribute significantly to this issue. 2. Types and examples of e-waste. E-waste can be categorized based on the type of electronic equipment. Below are common types and examples. 1. Computing devices, desktops, laptops, servers, printers, scanners, etc. 2. Communication devices, mobile phones, telecommunication equipment, etc. 3. Laboratory equipment, analytical devices, spectrophotometers, centrifuges, etc. 4. Consumer electronics, monitors, televisions, projectors, etc. 5. Storage devices, hard drives, USB drives, DVDs, etc. 6. Batteries, rechargeable and non-rechargeable batteries from lab instruments. 3. Sources of e-waste in laboratories. E-waste in laboratories originates from several sources, including 1. Obsolete equipment, outdated analytical and measuring devices, e.g. analytical ballaces. 2. Damaged instruments, equipment that no longer functions, e.g. phones, stopwatches, etc. 3. Upgrade of technology, replacement of older devices with newer, more efficient models. 4. Consumable accessories, used batteries, cables, and connectors. 5. Research projects, discarded equipment after research experiments. 4. Health effects of e-waste. Improper handling, storage, and disposal of e-waste pose severe health hazards. Common health impacts include 1. Exposure to toxic metals. Lead, mercury, and cadmium exposure can damage the nervous system, kidneys, and bones. 2. Inhalation of toxic fumes. Burning electronic waste releases harmful fumes causing respiratory diseases. 3. Skin contact with chemicals. Direct contact with toxic substances in e-waste can cause dermatitis and other skin conditions. 4. Bioaccumulation. Persistent toxic substances can accumulate in the food chain, posing long-term health risks. 5. Laboratory management of e-waste. Effective laboratory waste management systems for e-waste are crucial to minimizing risks. Key management strategies include 1. Inventory management. Keep track of equipment lifecycle and schedule timely replacements. 2. Segregation. Separate e-waste from general laboratory waste. 3. Proper labeling. Clearly label waste bins for electronic waste. 4. Storage. Store e-waste in designated areas to prevent contamination. 5. Training. Train laboratory personnel on safe handling and disposal practices. 6. Maintenance and repair. Regularly maintain equipment to extend its lifespan. 6. Disposal methods for e-waste in laboratories. Disposal methods for laboratory e-waste include 1. Recycling. Send e-waste to certified recycling facilities. 2. Donation or reuse. Functional equipment can be donated to other laboratories or institutions. 3. Manufacturer take-back programs. Some manufacturers have e-waste take-back policies. 4. Incineration. Controlled incineration with proper filters can be used, though it is not the most environmentally friendly option. 5. Landfilling. This should be the last resort, and only in regulated landfill sites. 7. Conclusion. E-waste management in laboratories is essential to reduce environmental pollution and prevent health hazards. Through proper waste management systems, training, and sustainable disposal methods, laboratories can significantly reduce the risks associated with electronic waste. Collaboration with certified recyclers and adherence to environmental regulations will ensure safer and more responsible management of e-waste in laboratory settings.